Hello and welcome to this manufacturing process technology part 2 module 30. We were talking about the role of melting temperature in EDM, and we showed and I actually shared with you empirical relationship that happens of the total material removal rate as a function of the melting temperature theta m. As you can recall that if theta m goes up or the material has a higher melting point, then obviously the material removal rate falls down in that particular case. So, we were talking about the role of dielectric fluid and how the circulation of fluid would alter the EDM process. If in an EDM process, if the dielectric is forcefully, I mean it is the dielectric is subjected to forced circulation in the machining zone, there is a tendency of the material removal rate to go up. And the reason that we were talking about mostly is that there is a formation of an ion column every time there is a spark, as we all recall in EDM, and then if the circulation is forced, there is a tendency to dissuade away that ion column quickly, so that the next can get formulated. And so obviously if the ion is or if the ion path is there still in the dielectric, then there is no generation of the spark, because it is a conducting column, and whatever electron excess would be there on one side would actually get conducted, and the electron would rather follow the conducting path to get shorted onto the anode rather than getting into a space and creating a spark or a plasma, which otherwise happens. So therefore, de-establishing the column or maybe taking off the column and the removal of the ionicity which has been occurred or which has occurred because in the dielectric fluid because of the sparking process is very important at every step. So between two sparks you have to ensure that the column fades away, or the total ions and electrons which have been generated, they should somehow be either absorbed at electrodes or go away from the machining zone for another column to get established. So this happens faster if the fluids are circulating in nature. In fact, let us look at a trend here of the material removal rate with respect to the advance of the electrodes for two different cases. One is with and without the forced circulation. You can always see that with advance of electrodes to each other, or a reduction in the Ig, the inter-electrode gap, you can always so this is the reduction in the Ig. Okay. You can always find that material removal rate is better or higher with forced dielectric fluid circulation. So the figure on this shows the nature of the MRR characteristics with and without the forced circulation. And after the discharge is completed, the dielectric medium around the last spark should be allowed to deionize, and for this the voltage across the gap must be kept below the discharge voltage until the deionization is complete. Otherwise the current may once again start to flow through the gap at a location of the previous discharge, and the time required for complete deionization depends on the energy released by the preceding discharge, of course. So obviously if you force circulation, then it is quickly dissuaded or dissipated. So a larger energy release would always result in a longer deionization time, which gives you some limitation about the sparking frequency. So that is how the whole material removal process happens. Now we have looked into enough of physics behind the EDM, and we have also gone across some of the empirical formulations regarding how the crater size can be defined in terms of, let us say, the height or depth of crater as well as the diameter of the crater. We have also looked into aspects related to the melting temperature of the material and how material removal rate gets affected because of the melting temperature of the removal. We have tried to estimate the crater volume of a EDM process given some of the empirical estimations of the diameter and the size of the crater based on the pulse power or the sparking power. Okay. So all this was done with an intent to really try to find out what is the overall MRR or material removal rate. And so everything in EDM is really about how good you do the charge transport and the charge delivery, and the electronic charge actually is responsible for all the momentum transfer, so that the MRR increases. So having said that, let us now try to look into some of the governing principles associated with how this delivery would happen, how you can do the quick charging, discharging of the IEG or the interelectrode gap, so that you can have more material removal rate. And for doing this, it is important to find out some circuits, associated circuits, or some governing laws where the electron release rate can be controlled as a function of time. So, one of the circuits which comes into our mind immediately is the RC circuit, the resistance capacitance circuit, where such governance can be administered of the electron flow process, okay, as a function of time. And so, let us look at some of these basic EDM circuits and operating principles, where we could even have these circuits operated at some parameters where material removal rate is very easy to find out based on what is the capacitance or what is the energy, spark energy that is delivered. So, several different electrical circuits are available to provide this pulsating DC across the work tool gap. Once the spark is generated, obviously, and the ion column is dissipated, then you are ready to go for another DC surge, where again another spark could take place. So, though the operational characteristics are different in almost all circuits, a capacitor is by and large used to do this charging, discharging action, and the way you are supplying to the capacitor is again a function of the remaining components like resistance, etc., or the internal load resistance of the power source that you are using in the circuit. And so, capacitor is typically used for storing the charge before the discharge would happen. Okay. So, how quickly you could charge, or how efficiently you could discharge, or at what criteria you could discharge, is really what would govern what is the MRR, or the material removal rate. So, the suitability of a circuit depends on obviously machining conditions and requirements, and commonly used principles are resistance capacitance relaxation circuits, which we will talk about in great details, because this is also another way of estimating MRR. You could operate this at a certain power parameter and also a distance parameter, through which you could find out what is going to be the tentative amount of MRR or material removal rate from the empirical relationships that have been generated earlier. There are of course rotary impulse generator based circuits and controlled pulse circuits, which are used with solid state electronics, etc., these days. And so, for the first basic circuit that comes into our mind is the resistance capacitance relaxation circuit. So, let us look at some of the analytical issues with such a circuit. So, the resistance capacitance relaxation circuit really is represented in this diagram here, where there is a charging circuit, as you can see, which offers the charging circle starting with the voltage V0 output voltage. A capacitor which is placed in between, which would be responsible for the charging and discharging if needed, and then at the first instance through the resistance capacitance on the first part of the circuit here, the capacitor is being charged up to a maximum charge value that it can hold, okay, and so it has some kind of a time constant associated with this whole charging cycle. Once it is charged, the dielectric fluid placed between the two electrodes here is somehow needed to be ionized, okay, by development of a spark, so that the charge on the capacitance can be dumped onto the workpiece. Okay. So, now what you do is to feed the tool, so that again the distance here between the tool and workpiece reduces, and the electric field goes above the breakdown electric field, where there is a sudden generation of the spark. Okay. So, now it is all about in the second cycle how this capacitor right here discharges through the spark onto the workpiece surface. So, that is why this discharging part is very important. So, we are going to do the analysis on two fronts. One is of course the charging circuit side, and another is going to be the discharging circuit side. And one must remember that there is obviously a very important relationship in terms of maximum power transfer between the source voltage and the interelectrode gap. You have done this in great details when we looked at plasma systems earlier during the first few modules in the microfabrication part of this lecture. So, let us look at now the charging circuit part. So, if we talk about charging voltage and charging current. So, the charging current We call this current ICT here because it is a function of time obviously, as the voltage, the potential difference is applied across this end, and the capacitor plate right here which is charging with the voltage of the charging capacitor VCT again as a function of time. So, the charging current ICT is related to this VCT through the expression ICT equal to V0 minus VCT by the circuit resistance RC, which is also a variable resistance, but at this time let us assume a fixed value of RC. So, that is how the ICT or the charging current is experienced, in which the charging the capacitor is being charged by the charging circuit. Also, if we look at the capacitive side and the way the voltage and charge varies, so the the current, the charging current ICT is also expressed as a rate of flow of charge into the capacitor, which can actually be recorded as CVCT, where CV, as you know, is equal to the total charge on the capacitor. So, the capacitor C's capacitance C being constant, we can record this as C VCT by dt. So, that is how you can record the ICT. So, this actually can be equated then as C VCT by dt equals V0 minus VCT by RC, and if we try to solve this problem, let us say, let us just mention all the parameters before going ahead. V0 is the supply voltage, RC, and that too supply voltage of the source at time t. RC is basically the charging circuit resistance, and C is basically the capacitance of the condenser. On the charging side or the discharging side. So, obviously from the earlier equation you have C VCT by dt equals V0 minus VCT by RC. So, you have dVCT by V0 minus VCT could be actually equal to dt 1 divided by CRC. So, if we integrate both sides, we have a indefinite integral ln V0 minus VCT equals minus t by CRC plus K1. K1 is the constant of the integration, and let us try to now estimate the K1 by looking at maybe one boundary. So, at time t equal to 0, we know that there is no charge, or there is no, so we know that there is no charge buildup in the condenser. In other words, we can say that the VCT, which is because of the charge buildup, remember Q equal to V times of C times of VCT is equal to 0. Okay. So, K1 therefore becomes equal to simply ln V0, and from this expression at time t equal to 0 you put VCT equal to 0. So, that becomes K1. In other words, we have the final expression written here as ln V0 minus VCT equal to minus t by RC times of the capacitance on the condenser C plus ln V0, or in other words you could write, or if you could just manipulate this equation algebraically, you have VCT equals V0 1 minus e to the power of minus t RC times of C. That is how the voltage VCT would be determined. In the interest of detailing, just wanted to mention the way that you solve this is ln V0 minus VCT minus ln V0 becomes equal to minus t by CRC, and so ln V0 minus VCT by V0 becomes equal to minus t by CRC, or if I wanted to just raise both sides to exponential. So, you have minus t by RC times of C e to the power should be equal to V0 minus VCT by V0. In other words, VCT becomes equal to 1 minus e to the power minus t by CRC times of V0. That is exactly what we arrived at here, just in the interest of detailing, although it is probably not related at the level in which this course is being operated. So, as we all know, the time required by the condenser to achieve around 63% of its charging voltage. So, therefore, 0.638 V0, okay. And this is called time constant. Tau, and this can be represented as RCC. Obviously, if t equal to RCC, VCT should be equal to 1 e to the power of minus 1 times of V0. This value is about 0.638. That is exactly what we are talking about. So, that is how you can actually find out from this RCC values what C times, or the capacitor of the condenser times the variable resistance of the charging circuit, what is the time constant involved in the charging part of the circuitry. So, as ICT is basically V0 minus VCT by RC, I can always substitute the value of VCT here as minus V0 1 minus e to the power of minus t by RC times of C divided by RC, and obtain ICT as V0 e to the power of minus t by RCC divided by RC. So, that is how you actually can know the value of current I as a function of time in the charging circuit. Okay. So, this value here right here ICT. So, the power delivered to the discharging circuit is now of importance to us, because obviously once the capacitor has charged, we would like to look forward to sort of the capacitor getting discharged through the IEG or the interelectrode gap, so that the spark can fall on the workpiece and start melting. So, the power delivered to the discharging capacitor or discharging circuit can be also mathematically or analytically found out. The energy delivered to this discharging circuit can be expressed as, maybe at any time instance t, can be expressed as Den, which is actually the current voltage product of the charging capacitor times of dt. Okay. So, obviously, the current voltage product is the power as a function of time, and we are talking about an instance dt for which an energy could be delivered, and so the amount of energy delivered would be equal to the current voltage product times dt, the time. So, if we look at the current voltage product from some of the earlier definitions that we had obtained in the last 1 or 2 slides, we would be really looking at Den as the VCT value, which is V0 by RC times of e to the power of minus t by RCC times of the ICT value, the ICT value, which is V 0 by R C times of e to the power of minus t by R C C, times of the VCT, which is V 0 1 minus e to the power of minus t by R C into C times dt. Okay. So, if we integrate on both sides again, integrate again with respect to time, the total amount of energy E n comes out, which has to be delivered from the capacitor all the way to the workpiece, and the product, this product can be integrated in time as V 0 square by the charging circuit resistance times of minus tau e to the power of minus t by tau. We assume tau to be the time constant CRC, okay, as just derived in the last step. So, I am just replacing this CRC everywhere with the value tau. So, minus tau e to the power of minus t by tau plus tau by 2 e to the power of minus twice t by tau plus the constant of the indefinite solution. Okay. So, constant of integration. So, we are going to find out or estimate this value based on the boundaries again. So, at time t equal to 0, as we know, the total energy that is dumped into the capacitor from the charging side of the circuit is E n equal to 0, and considering that to happen, the E n value really 0 becomes equal to V 0 R C times of, we can find out the K 2 value. This guy becomes equal to 1, and so does this. So, we have this times of tau by 2 with a minus sign plus K 2 equals 0, or K 2 is basically V 0 square times R C 1 by R C times of tau by 2. So, if we substituted this value back into this expression right here, we obtain a value of E n, which is equal to V 0 square by R C times tau times 1 by 2 plus 1 by 2 e to the power of minus twice t by tau minus e to the power of minus t by tau. So, this is finally what is the kind of energy that is dumped into the IEG zone or inter-electrode gap zone for doing the machining. Okay. So, obviously, we would like to get some kind of a average power based on the just division of this energy by the time for which this energy is dumped, or we can say the time for which energy E n is delivered to the discharging circuit. So, if T c were the total time for which energy E n is delivered to the discharging circuit, then obviously power average here could be E n by T c, and I can easily express by substituting the value of E n corresponding to the time t equal to T c here as V 0 square by R c times of some value x, where x we have assumed to be the time ratios T c and tau, tau being the time constant R c c and T c is the total discharging time for the capacitor, times of 1/2 plus half e to the power of minus 2x minus e to the power of x. So, that is how we can have an average power, and further we need to operate at the maximum power transfer condition, which says that the del P average with respect to, let us say, del x, which is the new variable here, the time ratio, equal to 0. So, we are going to find this out in the next module. In the interest of time, we are going to close this particular module, but the whole idea here is the the charging cycle, as you can see here. So, the charging happens over different and this is actually the discharging. Okay. So, as soon as the voltage of the capacitor goes to the sort of discharge voltage across the gap, there is going to be a discharge. So, the capacitor is not allowed anymore to charge up to its highest limit, and so there is some kind of a discharge. So, this whole time represented by red here is actually one charging time cycle. So, typically this is how the signal within the capacitor would look like. So, you have a charging time and then the discharging time, and the total time there is Tc. So, you can operate the capacitor many times at Tc, twice Tc, 3 Tc, 4 Tc, so on and so forth. So, that is how the instantaneous gap voltage across the tool and workpiece would vary, which is actually pretty much the voltage and how it varies across this capacitor. So, in the next module, we are going to sort of look at this average power and try to find out an operating point x corresponding to which this maximum power would transfer from the source voltage all the way to the gap. Till then, I would like to end this module now. So, till then, thank you very much, and see you in the next module. Thank you.